Готовились?
Power off.
Hi, everyone. First of all, I want to thank you for taking your time to attend to today's data science meetup. Добре. Hi, everyone. First of all, thanks for taking your time to join our meetup today, where we're gonna talk about autonomous cars, a very, very hot topic for the last recent time. First of all, I want to share a few words of for the organizer, who are we and what we do. And then we will introduce the lecturer and give the word to Yordan to share what he has prepared for you. So I'm part of a Data Science Society. This is a group of data enthusiasts, and what is common about all of us is that we're very keen on data science topic and want to learn more and share more. This is a voluntary organization, and if you visit our page, you'll see who are the people in our team. You will see also the regular yearly datathons that we organize, where we have attendees from about 20 plus countries, and last year we had more than 700 registrations only for the Maze Datathon. So in case you want to become part of our team, just drop us a note in either Facebook or write us an email, and we'll talk. However, enough about us as an organization, and let's go a little bit more on the essence of today's meeting. So today we will talk about autonomous cars, and we will have our lecturer Yordan Darakchiev, who is an expert in this in the area of machine learning and data science. A few words about Danchu. He's currently doing a PhD in Astrophysics in Sofia University, has quite broad and stable experience in the field of machine learning, and is currently also working as a machine learning engineer with focus on image detection and image classification and computer vision. What he says about himself is that he was teaching as well as people, but also computers. So recently he spoke a little bit about medical details and the application of machine learning in medical domain, and today he has prepared to share with you more about the autonomous cars. What you will hear today, the pros and cons, some comparison, what different types of approaches, how do we approach biases, and what could be the issues with the data. One of the most important thing in this area, how to ensure people's safety. Training models. Lecture will include public data, some code and sharing of some training models. But enough from my end. I'll give the word to Yordan to share what he has prepared for us and give us more insights on the topic. And in the end of the meeting, we'll go through all the questions that you may have. By the way, since we are streaming directly in YouTube, you can share at any convenient for your time your questions as comments under the streaming, and we'll try to reply all of them in the end of the meeting. So, Danjo, thanks for accepting our invitation, and the mic is yours.
Thank you, Jana. Thank you, Data Science Society, for having me today. It is an extreme pleasure always being with you. And it's actually my second time here. Last time I talked about astrophysics, machine learning in astrophysics. It was quite a long time ago. And now I'm going to present something which is maybe a little bit more practical and I hope a little bit more relevant to what we are doing daily. Just please, if you can see my screen and when you can see my screen, because I'm not exactly sure I'm sharing it now. Is my screen on? I hope it is. And it is now. It should be. I'm seeing the endless recursion here. It should be presenting now?
No. Sorry.
Oh, okay. Okay, sure. So, yeah. Hello, everyone. You already understood a little bit about myself. You got to know me already. And I'm going to present a little bit of theory and a little bit of practice about what is a very hot topic or a very cool topic, pardon the pun, right now, which is self-driving cars. I happen to have a little bit of an experience in the field. I've worked on, let's say, something like that previously, and I'm looking forward to be working more on that in the future. It's a very nice field, but also really challenging. I could compare it to sending satellites into space, because you have that same kind of constrained environment. Then you have to take decisions very quickly and ensure people's safety, which is of utmost importance at every second. So it's very interesting. It's also not diseases, because I saw that a few of the people that I presented in front of were quite grossed out of the thought of diseases, especially chest X-rays, as I used to talk last time. But hey, let's focus on self-driving cars now. Well, I'll try to split my talk into two parts, and I'm hoping that the first one is going to be much shorter, which is going to be more theoretical. But in order for that to happen, I'm relying on you having some knowledge about neural networks and TensorFlow in particular. In the second part, I'm going to walk you through several of the steps how you can get started. And I'm hoping that at the end of this call, or maybe tomorrow morning, or whatever time zone you are, you can go ahead and try it out yourself. Because, of course, we can't reproduce all of the state-of-the-art results, but we could still hope to learn something. Sorry?
Sorry to interrupt you, but I think that we're seeing that you're presenting, but it's not the presentation that you're...
I don't have a presentation.
Okay.
I'll be using my browser.
Okay.
So I'm currently on the tab with the call, and I'm going to very quickly turn to something else. I just wanted to make introductions. Yeah, it's a practical session, so there is no time to switch between PowerPoint and something else. I'll be using the Blackboard, of course, for at least a few minutes. Okay, so I hope I can take questions, but it will be more convenient for me to answer at the end of the call because I'm not able to see any sort of questions. You're seeing my entire screen, and I may be unable to see what you're asking live. Okay, so let's start from the beginning. We work with images, and this is not directly related to self-driving cars. So working with images has its own specifics. For example, an object in an image is localized. If there is, if my avatar is a tiger, you see a tiger here where I marked it in red, but this part is also a tiger. A part far away from that is maybe not a tiger. And this is something called locality. And it's the main thing that our main algorithm called a convolutional neural network exploits. So I'll be hoping that you're a little bit familiar with convolutional neural networks and go to the heart of the problem: object detection and semantic segmentation. First of all, let's see what that looks like. This right here is an object detection task. So you have an image, maybe taken from the dashboard of your car or a dash cam or something. This image contains road, maybe some pedestrians, maybe some cars, traffic lights, and a lot of other things, buildings. It may include sky, it may include something else. The task for object detection is exactly what you're seeing here. Take each object and draw an axis-aligned rectangle around it. This rectangle has 4 coordinates, the coordinates of the top left usually corner, its width and its height, and also it has a class, which is one of a fixed set of classes. So you can see it's a very nice blend between what we call classification and regression. And when we train our models to do object detection, we have to mix the regression of coordinates and classification of classes for each bounding box, as it's called. So this is it now, but there's a few details missing here. For example, I'm not seeing an object detection instance, an object detection label for the road. I'm not seeing one for the crossing. I'm not seeing one maybe for the billboard, for the building, etc. And this is a very key part of object detection. You may have many different objects, but necessarily you do not label the entire image. On the other hand, semantic segmentation is exactly that. What you're seeing here is an image overlaid with some colors, let's say. Each different color corresponds to a different thing that the image is showing. So you can see the road has one color, vehicles have other colors, people, and please take note of that, people have the same color. So we can see if something is road, vehicle, traffic light, or person. We cannot still identify persons or identify individual people, sorry. If we were able to do that, the task would be called semantic identification or just instance segmentation. So I just want to point this out very quickly. We are not going to talk about instance segmentation. We are not going to try to pick up individual vehicles or individual people, although this might be important as well. We're just going to compare those two approaches. So this is what this output looks like. But what would that look like if we had a model? So we pass an image and we get another image. Imagine this. Keep the contents of the image outside of your mind for a second. Imagine only the colors. Well, isn't that an image? And by the way, isn't every color something like a class? Can I assign, for example, a value 1 for the road, 2 for a vehicle, 3 for a sign, 4 for a traffic light, etc.? Well, I can. And I'm going to get a very strange image, but an image nonetheless. So I could view this problem for a completely different perspective. And that is image translation or image to image. I pass an image containing a scene on the road, and I expect back something which to my model looks like an image, but I can interpret it in a different way. Said more simply, you can think about semantic segmentation just in the same way as we did object detection, but this time every single pixel has its own class. And by the way, we have to still obey locality, because if those pixels represent a car, the pixels next to them can't represent something else. For example, the small region can't be a part of the road. So there is still a constraint on locality here. Okay, so these are two completely different approaches. Which one should we use is a very important question. It turns out that this question is unsolved still, especially in the field of self-driving cars. Because you see, there are many pros and cons to each one. For example, object detection can be very, very, very fast. Okay, especially if we have a limited amount of objects. Let's say we don't care about any more cars than 5 on the road. We just want to see our nearest 5 cars. We don't care about more than 20 people, let's say. We could constrain the problem so it's very fast and very reliable to perform, to train a model on, and maybe to make a reasonable inference. Semantic segmentation allows us to be much more flexible, but it takes a lot more time. And why is time important? Well, let me tell you. Usually when we do object detection, let's say I have quite a lot of experience with traditional models, which I'm going to talk about very briefly in a few seconds. And those traditional models for object detection usually take about a second or 2, or a couple of seconds. They may take 3 or 4 seconds in very rare cases to predict a very simple image. Well, keep in mind, this is on a very nice hardware. For example, it may be a Tesla V100 or something. How about this? We are in a car. Our car has a battery. We don't have an infinite supply of electricity. We don't have an infinite supply of hardware. We have to run our algorithms in a very constrained environment, 1. And 2, we have to be lightning fast. Imagine what would happen if each self-driving car only takes decisions once per second. It would be a disaster. The human response time, by the way, is about 1/10 of a second, or it could be even less. A drunkard's response time may be a second or more, which for comparison means that if we don't constrain our performance, by performance I mean runtime performance, execution time, our self-driving car is going to behave like a drunkard on the road. And we do not want that. So here's the thing. This one provides better results. This one works a little bit faster. But even that could be really, really slow. It depends on the accuracy, of course. And of course, we have to take other things into account. For example, there is the time to acquire an image. So for example, let's say there is a camera on the dashboard. Then this image has to get wired through to the car's computer. it has to get processed. Something will have to interpret the results, and after that, those results will have to maybe translate into actions. Okay, then. Well, this might be a problem. And there are other things, other ways to try to mitigate that problem. One way is, for example, okay, what happens if our models perform very poorly? We as people have two eyes. Can we have our camera have two eyes? Well, of course we can. We can put two identical cameras, calibrate them very precisely, and they will give us a stereoscopical image, which means an almost 3D image, which is very nice, which makes us aware of our surroundings, etc. But we have to cut the processing time in half, which is very unfortunate. Okay, how about other systems? For example, see, if that's an image taken by a camera, don't we have other information as well? A driver has rear view mirrors. A driver has ears. A driver even has the other senses they can use. While our self-driving car is going to be really, really constrained if it only relies on a front-facing camera. So how about getting other senses into our cameras, into our cars? Well, we can do that. One of the most popular systems is called Lidar, and it gives you basically a 3D overview. So if you superimpose an image and the Lidar, it's called the Lidar field, which is basically a depth sensing image, you might see, for example, each pixel and how far away it is. So, for example, you know that this is, let's say, 20 meters away. The building is 100 meters away or something like that, which is good. But it also increases processing time. And we are trading on this very, very, very sharp edge between performance, reliability, and speed. And all of these have to be taken into account. But keep in mind something else. Computational power doubles. Well, okay, Moore's law doesn't hold that well already, but still we're expecting to have much better hardware. By the way, speaking about hardware, I have to add something else to the dilemma with self-driving cars. By the way, two other things. So the first one is, imagine what happens if a fully autonomous car, one which doesn't rely on a driver at all, crashes on the road. Has anybody had their computers crash? We are having that all the time. One might say if you're using Windows, which I am, but that's another topic. Well, what happens if the AI unit crashes? And even worse, what happens if somebody hacks it? Because we've already seen that. We've seen adversarial networks which can do something like that. For example, they may change the labels for, let's say, people to roads. And if a car mistakes a person for a piece of the road, it's going to run them over, which is, let's say, not optimal. And the final and maybe most important problem, okay, not final, but final in what I'm going to discuss. Maybe most important problem is the so-called X factor. No, I'm not going to talk about musical shows or something like that. I'm going to talk about the human factor. It's widely known now that in a perfect world, maybe a few decades from now, where every car is autonomous and every car could talk to each other, if we assume good intentions, so for example, if we assume that those cars aren't hacked, we could be sure that they will perform really, really well. They won't need to have, for example, turn signals. They won't need to have pedestrian crossings even. All of the things that we take for granted driving a car were made and engineered to prevent us from killing ourselves or others. Taking a person outside of the equation actually could solve a lot of the problems. But is that feasible? Probably not. Until then, we are stuck with the most important and maybe most problematic aspect of it all. The X factor, the human factor. The factor which perpetrates through every single aspect of what we are doing. Not only the driving, mind you. Who creates those models? People. Who creates those data sets? People. And what do people have? Biases. I was very cheerful. I shouldn't be that cheerful talking about this. Sorry. I'm just excited. So, how do we deal with that? There are many ways to approach the problem, and the most important of them is sharing our data and our models, having them be open to review, having them be available to the public to test, to improve, to validate, to review, etc. And by the way, this is not something uncommon. So if you look, for example, for Tesla incident, or maybe Tesla car incident, you're going to see accident. Sorry, I'm very, very, very bad at English. So have a look. 2021. There are other accidents like this, maybe about 10 a year. And Teslas are very, very, very expensive cars, which very few people can afford, which means that very few people drive those. And even fewer people can afford autonomous driving capabilities. So actually, those things could be much more ubiquitous than we were expecting. And this is something that we have to look out for. And of course, we have to look out for being able to recognize people, being able to stop on time, being able to steer our car in a particular direction, etc. And this is necessarily a joint effort between scientists who develop the models, people who drive and generate the data sets. So, for example, what if the data sets have a hidden bias? And one way of having bias would be, for example, the city that you're traveling in. So imagine an European model, something trained on German data, French data, maybe US data. Imagine this car getting into England and suddenly having to drive on the left. How would we guarantee any sort of performance? Well, we can't, is the short answer. Also, there is something else very recently, and I'm very sad that it still happens. And this is that self-driving cars seem to miss people of color. They seem to draw a box around a person. What that means is the car doesn't know there is a person in front of it. And you know the consequences of that, the implications. And by the way, I worked with something like that. I'm also working on model explanation. For example, why did you take a right turn is a question which a lot of might want to ask a self-driving car. Why did you take a right turn? Why did you get into the sidewalk? Why didn't you stop on a red light? And these questions have to be answered very carefully, because it comes down to safety. It comes down to saving lives. And that's why I said that it's no less difficult than sending spacecraft into orbit. Because you see, spacecraft is usually really expensive. It's usually the result of many years of deliberate scientific work. But those things are usually unmanned. And in the worst case, if it crashes, it's much more likely to crash somewhere in the ocean. Not that this is good, but at least it's highly unlikely to kill somebody. Now, imagine a mid-sized city where a third of the cars are self-driving. How many ways are there to create an accident? How many ways are there to break the law? Is the law relevant to self-driving cars? All of these are questions that remain open. But now we're going to focus on the practical aspect of things. So, you can see this is a problem description. But let's have something else in mind. Usually, with self-driving cars, or autonomous vehicles, if you want the more posh-sounding version, it doesn't simply come down to image analysis. Because what does this analysis give us? Maybe nothing by itself. This analysis has to be used in some way. And there are many different tasks to approach. For example, one might be what's called lane detection. Your algorithm doesn't have to know anything else. It just has to segment your driving lane. And the result of that feeds through a model which tries to correct your position, maybe using the steering wheel, to remain at the center of the lane. So one thing that you might want to do with this analysis is lane detection. Another very important thing, so important that usually AI units have a different part of the hardware doing that. This is pedestrian detection. So, for example, a common case would be if an algorithm is trained on data, it's only trained on seeing people walk around, maybe cross some crosswalks, etc. Would it recognize a mother with a child walking by? Or would it recognize a stroller? Because a stroller is not something which is in this set of classes. Imagine this situation. What would that look like? Is that a car? No, of course it's not. Is it a person? No, it's not. If we fail to put a bounding box, a car may decide to run through the thing. So, pedestrian detection is also really important. Traffic lights and recognizing the signals from traffic lights is also very important. A task made quite a lot more complicated when you take into account the fact that on very big crossroads, there are tons of traffic lights. So a vehicle has to, first of all, find all of them. Second, filter out the one that is relevant to it, because not all are. And sometimes there are multiple traffic lights showing the same thing. It might get really confusing. So these are some of the most important operations here. And maybe the most common one, the most, let's say the most classical one, the one that has been around for ages, even I think from the 1990s, using very, very simple neural networks back then. This is automatic steering, which seems to be a very, very, very simple problem, but one which, first of all, is really important. The second is really hard to train, really hard to solve there. So what would that mean? Let's say take an image and as output produce the degrees that you have to turn the steering wheel towards. For example, 10 degrees to the right or 2 degrees to the right. You may also have other outputs such as how strongly to press the accelerator pedal or how strongly to press the brake pedal. All of those could be different outputs. But then we are going to think about something else. How could a self-driving car drive using images? Well, it can't. This is impossible. This is absolutely nonsensical. It has to drive using videos. And those videos, you might treat them as sequences of images which are independent, but this is going to take you more processing time. They are not independent. So if you have a sequence of frames like this, a sequence of images like this, can you exploit what you've seen previously, what you've computed maybe a tenth of a second ago, to reuse it in the next frame? Well, sometimes, because sometimes things change. And once again, we're trading in a very difficult territory. Because if you want to be lazy and not reevaluate too often, we might get an outdated version of the road. And most things happen very, very quickly. So there is this other point to consider. But is it possible at all to then create a self-driving car? For now, maybe just in a lab, or using GTA or something as a training field. But have a look at this. This is one very recent paper from NVIDIA. And of course, they have produced perfect results. By the way, I'm going to talk about intersectional union if you don't know what that is. And if we see, I'm not going to play the video because it's a little bit long, but see, those predictions seem to be really good. What's the catch then? Well, the catch is that we are not NVIDIA. And we are not able to produce those enormous models and provide them with maybe hundreds of hours of training. What we want to do is to learn something and try something out for free, which might be a problem, but not so much. What we want to do is get our hands dirty and try out different things, try out different models, different approaches. And the classical approaches can be summarized from those 3 places. The absolute standard in object detection is called faster Rcnn. R comes from region proposing convolutional neural network. And this basically boils down to having anchors, predefined regions, let's say, which are then matched to the image. And if there are objects matching those anchors pretty well, they get marked. They get their borders. After that, they get their classifications. So this seems simple enough, It is not. It actually is quite a lot of work to implement. But this is the standard. Maybe not state of the art, but standard when it comes to object detection. The problem is, even though it's called faster, before faster there was fast Rcnn, it's actually quite slow. It is extremely accurate. It performs extremely well, but it's quite slow. So, a different approach, which has necessarily lower accuracy, but much better execution time, is called YOLO, or You Only Look Once. This is once again a convolutional neural network, which has the same kinds of input, an image, an RGB image to be precise, and the same kinds of outputs, boxes, and their classes. Once again, I'm reminding you, a box is described by 4 numbers, between 0 and 1. And its class is one of many predefined classes like person, traffic light, road, sign, traffic sign, billboard, something else. Okay, so this is the competing architecture. By the way, yeah, those articles are really, really long, but they're worth reading. If you're really into object detection, I'm certain that you have to read those and get acquainted with them intimately. How about the other approach? The one that takes an image as an input and produces another image as an output. The classic here is called a UNet, for reasons that are going to become apparent very soon. Look at the shape. That's why it's called a UNet. Of course, if this is your first scientific paper that you look through, you might say, okay, this is very difficult. I am not able to do that. Let me tell you, it does come with practice. So this is why I'm going to try to walk you through the basic steps along the process, along the path, because they can be really frustrating sometimes. Everything from learning, from reading the scientific papers, getting the results, getting data, trying to run the code, which should work but doesn't. And I'll be trying to make the process as painless as possible. Still, keep in mind that the first time is probably going to take you a few days to run it, especially if you haven't done something like this before. But is it worth it? Totally. Okay, so this one is a little bit simpler. You might see that if you're familiar with convolutional neural networks, you just have a fully convolutional architecture. No dense units, no attention, no dropout, nothing else. By the way, speaking about attention, it's becoming very popular and we're going to see many more representations, many more uses of it. By the way, the NVIDIA model that I showed you is an attention-based model. But still, let's stick to basics because we don't have the resources to run the big model. But we still want to run something and we'll be able to. Okay, so we have the basic tools under our belt. We know that either this approach or this approach would give us the results that we want. We might want to try and find some code, maybe for our favorite deep learning framework. This is TensorFlow for me. For others, it might be PyTorch or even something else. Those two are the most popular ones. PyTorch has something called Detection, which includes all of those models. TensorFlow has a repository called Models Research that I'm going to show you in a few minutes. Okay, now, how do we get our data? Because, okay, we could find some algorithm, For example, if I look for faster Rcnn Tensorflow, I'll see that there are many implementations. And for example, this is one which is not by the Tensorflow team, and it's from quite a while ago, which is going to be a problem. But hey, I found something. If I look more carefully, I'll find a better thing. If I'm looking for YOLO, for example, I can find something. And I can, of course, clone the repo and start it. In theory, at least. Not in practice. But let's say that. First of all, though, we have the model. But what should we model? One approach is to buy a dash cam, go driving around, and label our images, which is an excruciating amount of work. Luckily, especially this year, and maybe 2020 as well, we saw a lot of people and a lot of companies presenting their data for self-driving cars that they're developing, which is absolutely amazing. Up until very recently, the field was absolutely, let's say, stopped. It was unable to move forward because of lack of data. It was frozen in its tracks. Now we have a lot of data sets, a lot of good and well-segmented data sets. One very famous one is called Kitty. Karlsruhe Institute of Technology and Toyota Technological Institute at Chicago. This is where Kitty comes from. And this one has actually a lot of data sets for a lot of things that you might want to do. For example, you have the road segmentation. So you see, this is a semantic segmentation task, sort of, where you have a label, let's say 1 for the road and 0 for everything that is not road. Okay, that's good. Or you can even narrow it down to your own lane. You could have an object detection, which is the classical thing that we talked about. Or you could even have object tracking. You could have optical force, etc. And this is a dataset which is open, and it's pretty readily available. We're going to use something a little bit different because it's maybe formatted a little bit better. And I'm just going to show you a dataset called Cityscapes, which contains a lot of different things, but what we are interested in, are those two folders with images. Let's see. This is called left image 8-bit, and here we have many cities. By the way, here I've taken a subset of all of the cities just because we may not have the computational power to maybe run all of them. The entire data set is about 8 gigabytes zipped. By the way, what does a left image mean? It means that it's a stereo camera, and this is only the left eye of the stereo camera, which is what's called a mono image. Okay, let's have a look. Well, these are good, and they seem to be really interesting. And you can see many different things. You can see many different situations. And also you can see that the image is pretty big, which is really important because if we want to have a high resolution object detection, if we want to find small things on the road, for example, like, I don't know, traffic lights, maybe some stone fallen on the road, bumps, we have to have a very high resolution image, which brings us back to performance, but that's another topic. Okay, so these are pretty good. what does the segmentation look like? Well, you might have already guessed it. It's just a series of images. And I'm going to look at Cologne as well. Okay, so you can see here that on this data set, you have several annotations, as they're called, for the same image file. The one that you might want to work with is maybe the JSON file, the polygons file. The one that is best for visualizations is one with colors. So for example, if you compare this to what I had before, which I'm not going to search for once again, you'll see that it's quite a good description, even though it might be a little bit janky on the edges. So here you have many different things, train IDs, label instances, and do you see that this is a black and white image? And each label has its own number. If you go and parse it, you'll see something like this. So for example, I've loaded the images and I might be able to show it to you. So for example, if I see the first image, oops, I meant to write IMShow. We get file not found. I apologize. I might have changed the folder or something. Okay, I'm not going to get into more detail here because I don't have enough time. But you can see that you have label IDs, which are numbers starting from 0 to, let's say, 13 or 14. And each of those are classification pixels. If you look through the documentation, you'll see this file. So you see you have the ego vehicle, which is your own vehicle. Things that are just not part of the road, but part of the image and calibration. You have road, sidewalk, wall, fence, traffic light, traffic sign, etc. If you look at those train IDs, everything that is not 255 or -1 is something that we might want to use. For example, our road gets a pixel value of 0. Okay, that's very simple, because then we could have our image translation done directly. So the output would be an image with the same size as what we have as an input, but the values would be between 0 and, let's say, 15 or 18, depending on what you want to have. So for example, you might want to treat all of those vehicles as one class. This is up to us. So yeah, of course, you can transform your data. Okay, and then it becomes very simple. And even you could find something on Kaggle, which is doing that. This is a notebook which I forked from this user, which I'm not going to butcher the name of. And if you know TensorFlow, you'll see that it's extremely familiar. Reading files, preparing training and testing sets, reading images, data augmentation, cropping, and normalization. Mini-batch grouping. TensorFlow dataset with mapping for loads. Well, everybody is doing that with TensorFlow. This is absolutely common, absolutely known to everyone. Okay, so we could create a UNet model like that. Keep in mind that if you've only known about sequential models so far, a UNet is not a sequential model. So you have to use the model API, not the sequential API, which makes things just a little bit more complicated, but not more so than they should be. It's still very simple. what is complicated here is the sheer amount of code repetition. Let me tell you once again, just between you and me. Do you see similarities between this block and this block, for example? Of course, if you don't, please get your eyes checked, because there are similarities. And what do we do when there are similarities in the code? We extract functions. And then, instead of getting all of this wall of code, we'll have 12 identical function calls. And we'll be done. That's it. This implementation might look really scary, but keep in mind that, oh, come on, please open. I said, please open. And it did open. You see that it looks pretty scary. For example, this first layer is connected to the last layer, but that's common. That's what makes the U. Keep in mind that complex things are just many simple things glued together. And this is it. What part of this do you not recognize? If you have any experience with convolutional neural networks, you know what conv2d is. You maybe have heard of batch normalization. Even if you hadn't heard of conv2d transpose before, it's a matter of seconds to Google it, and a matter of minutes to understand that conv2d transpose is the same as conv2d. It's usually used for increasing the input volume. Okay, so if you know neural networks, this is absolutely available to you. And by the way, this is running on Kaggle. And this is really simple to run on Kaggle. Take this example. I haven't yet written a single line of code, and I have something working, which is amazing. Okay. And by the way, yeah, these are the ground truths and the predictions, and you can see they're not perfect, of course, but they're pretty good. Can you see something else here? Because I can. The images have been resized. And this is something very important for two different reasons. One, performance. Two, using transfer learning. We are not so crazy to train our models from scratch. We want to be standing on the shoulders of giants. And that's why we're using pre-trained models as the backbone of our model, if you will. This one is using one called Mobile Net version 2. And by the way, here's the thing when using a pre-made model, a pre-made function, you don't have to know the details. You have to know the details of UNet because you're implementing it. But we are basically stealing half of it. Okay, it's perfectly legal, but you're stealing it in a good way. And you don't have to know how it works. It's a black box. A black box which does what it's supposed to. And what it's supposed to do for transfer learning is take the image and produce what's called a feature map, a 3D convolutional volume, which contains your features encoded in a way that the neural network understands them. By the way, you might be familiar with something called encoder-decoder, and you can see that a UNet has very much in common with this sort of architecture. Okay, that's it. But UNet, as we saw, was quite simple. So simple, in fact, that we were able to implement it from scratch and train it. By the way, you can see the training is left with the default parameters. There is not even any hyperparameter tuning. It works because it's a very robust model as well as being simple. Okay. How about object detection? And luckily, what I'm going to talk about generalizes very well. Because when we go to production, we have to rely on code which is written by somebody else. And this somebody else might not have the exact specifications and conventions that we have for writing code. And also, if we rely on different libraries, we usually get into the complexity of it all. So if we want to use an external library, we have to know a few details. Once again, my favorite deep learning network, favorite for many reasons, by the way, is TensorFlow. So I'm going to show you how to get started using TensorFlow. Keep in mind that you can get started without writing a single layer this time. Basically, the model is there. The way to train it is there. You just poke it around, kick the tires, try different things out, and produce something as a result. What are you going to need? First of all, you're going to need some data. And data can come from many different places. It might come from those data sets, or in the case of object detection, you might use some software which does that. I will actually try to show you something just to see that sometimes it's very easy to get started. Let's open a random image. Let's say we're doing object detection. And let's say we want to detect different things. I just closed my annotations, which is extremely stupid of me. But let's say we want to label this as being a car. We want, I'll input them all. We want to have people as well. And I'm not seeing anything else here. Maybe traffic sign. Let's accept this. Okay, so this is a car. We're done. This, oops, sorry. I'm not very well coordinated. And one of the reasons is I can't use my mouse right now. Okay, I'm not going to label all of the cars here because there are a lot of them. By the way, keep in mind, there might be some overlap between the boxes, and that's perfectly fine. But see, we can get the data somehow. Then I think this is a person. I'm not going to label him as a car. This is a traffic sign, I think. And this is another one. There is another one next to it, but I'm not going to bother with it. Okay, so what do we do now? We go to Actions, Export Annotations, and if we want to work with TensorFlow, the VOC, Pascal VOC format, is the one that is going to be the most convenient. And here's what we have, an XML document, which contains a file name, the path, some information about the image, and information about all of the bounding boxes that we drew, with coordinates in pixels. Then we have to translate this to what TensorFlow recognizes. Because why would it work with something that is widely accepted as Pascal VOC? No. It has to take its own format. By the way, that's for a good reason. And the reason is performance. So fortunately, in this repo, which I'm going to show you very briefly, there is nice documentation, and it tells you how to proceed. So first of all, you have to create a file explaining all of your classes. It is called a label map, and it looks like this. Second of all, for every one of your images, you have to produce a file which looks like that. This code works as it is, but you have to provide the data, for example, height and width, hard-coded here. You have to parse the XML file, read it, and transform it. By the way, yeah, nobody wanted to bother with data preparation, bother with translation between image formats, but hey, that's life. We are doing AI. We want to make self-driving cars. We could tolerate a little bit of a data preparation work. So we take this, and this file, which is returned here, could be saved very easily as something called a TF record. And this is the file format. You can see this, this sort of document here. What else do we need? We need the models, the TensorFlow models repository, which I've cloned here. And this is extremely useful. And by extremely useful, I mean it contains absolutely everything that Google and their collaborators have done for us. It has models for many more things than object detection. But what we're interested in right now is the research folder and object detection. Now, if you're using Anaconda like me, which is the easiest way, by the way, to get this going, you have to take this object detection folder and place it preferably where your TensorFlow is installed. For me, this is my Anaconda directory. This is going to be long. Environments. TF2 is for TensorFlow 2 is my environment which I'm working at. Keep in mind there is libs, and a library. We are looking for lib, I think. Site packages, TensorFlow, or preferably TensorFlow core models. So you have to take this and copy it over to make it essentially a part of TensorFlow. Could we skip this step? Yeah, we could, but we have to play around with more things like Python paths and more dependencies. This is the easiest way to do that. Clone the thing, the entire repo, take only the models, research, object detection part, and copy it over. After that, you have to install it. And how do you install it? Well, it's written in the description, but also I'll give you some hints. If you're using Windows, you have to install something called PyCocotools first. And this is a real pain to install. But it will be very, very easy if you just know one thing. Install Visual C++. Look at Visual Studio installer if you already have Visual Studio, or if you don't, download Visual Studio, or download at least the Visual Studio build tools. And download the package called Visual C++, desktop development with C++. When you're done with it, you're almost ready. Then you can install Cocotools in the same way that is described in the documentation. Otherwise, PyCocotools would not install on Windows. I have tried it many times, and I have suffered many times. This is your easiest way. If you're using Linux, all of this could be skipped. PyCocotools installs because Linux, for some reason, has those libraries, those binaries compiling C++ code by default. Okay, this was the hardest part, I promise. Now, keep in mind that those object detection things present an API, which means that they have a ton of things going on internally, but you might need a very small part of them. one very important note. It depends whether you have TensorFlow 1 point something or TensorFlow 2 point something installed. Some of the models here do not work with TensorFlow 1. Most of them, and some of them don't work with TensorFlow 2 either, which is the most important thing here, because the recent version doesn't work with all the models. But most of them, those that you might be interested in, do. Okay, now how do we get to work with all of this thing? Well, there is a very simple file called model main. If it's called a main file, it's probably what we want to do. And by the way, this is my version. So I've done a few things to this file. This is sort of my fork. You can see some flags. You can see a main method, which you can call. And everything is described here. All of your settings, all of your paths to show are here. Okay, so you're going to want to run the model main in order to train your model. In order to make in order to make an inference, it's quite a lot easier. But how do you train? You have the data ready, right? You have to prepare the configuration first. And second, you have to find a pre-trained model to start from. Because, once again, we are not starting from scratch, especially when we have a small amount of data. And these, I promise, are the last things that you will need to do. I know I'm running short on time. So, first of all, you can have a look at this G3doc folder, which includes all of the documentation that you might want to know about. I've seen that for my practice, it hasn't been enough. I've used other things. I've used other approaches like scanning through the source code, but it works. So have a look at this one, TF2 and TF2 Detection Zoo. This is a list of all of the models and their performance and their size, of course, which you can use in order to get started. These are what's called model checkpoints. Those model checkpoints are there to help you start. They have been trained on different images, and you're using them as a transfer learning starting point. Let me tell you, these ones, faster Rcnn with ResNet 50, are the ones which are the most simple to use, and also they're very efficient and they perform very well. You can see the speed, which means that, of course, bigger and more complicated models are going to take more time. And you see the basic metric here, which is mean average precision, which is the metric commonly used for object detection. No matter whether it's segmentation or not, keep in mind that what we already have talked about, intersection over union and mean average precision, are absolutely correct and absolutely valid there. And for example, if you don't have, okay, let me go through this very quickly. You have in the green box your label, your prediction. In the red box, you have your ground truth. Their intersection is here. This is where the ground truth intersects with the prediction. The union is the area of the entire shape. This is intersection over union, one number over another. If it's 0, we are very far away from the truth. If it's 1, they're completely overlapping. We want to strive for this to be as high as possible. How do we go about segmentation then? Well, treat each pixel as its own box. And for example, if you have a funky ground truth like this, and a funky detection like that, their intersection is the number of pixels which are there. And the union is the total number of pixels under those shapes. Done. Ready. We're using the same metrics. Very cool. So have a look at those and maybe download one of them. I could show you what they look like, I think. Yeah. So for example, faster Rcnn with Rcnn trained on a dataset called ImageNet looks something like this. The entire thing is here. This file can be loaded very easily with TF model load, and you have to specify the path. You could even omit the model. TF load is enough, and you get the model. It's ready. And also you can specify the path to it. The last and most important piece of information that you need is the configuration file. This monster right here provides every single possible setting to your model. And what you will see at first, because this one is taken from the documentation, it's a template file, you'll see a string called path to be configured. And you'll see that in different places. Have a look. You have a trained input reader. I'm wondering, what does this input reader do? It may be reads inputs. So how about passing all of our newly created TF record files here? So we specify the full path, another full path, etc. So here you specify each individual path to TF records that you want to train on. Don't forget the label map. The entire purpose is to translate between the number 1 and the label road, the number 2 and the label person, for example. It doesn't have any other reason to exist. If you want to do validation or evaluation, you could also specify the paths to the images and maybe reduce the number of examples. So for example, if you have 50,000 images in your evaluation dataset, you might want to only use, let's say, 500 of them on every evaluation step, and then you have to shuffle them, because each time you will use a small but different subset of those. This right here is the most important part. The other parts are the model hyperparameters. And there is one hyperparameter which is extremely important, and this is the place that you are starting from, which I am not able to see right now. It should be somewhere in the train config. There we go, fine-tune checkpoint. This is the last path set, and if you save this file, if you run model.main and pass this file, which has all of the information that you need, you will get a model that is training. And this is it. It is a ton of work to get started. But once you get started, it's very easy to continue. Because let's imagine, for example, you might want to, you have, let's say, 300 images. By the way, a small piece of advice from me. Try to have very, very, very small batch size at the beginning. And maybe try to overfit a very small batch size, just to a very small number of images, just to see if the model works at all. Okay, now you've trained the model. What do you do next? You optimize it. How do you optimize it? Well, you go through all of these hyperparameters and start digging into them. By the way, these are not all of them. The default ones could be skipped here. Why do you know about hyperparameters? Well, there is the documentation and there is the code in TensorFlow models. But you can get started very easily. After that, it might get hard. You already know that. You might want to do some learning rate scheduling. You might want to present different anchors. The anchors were the default, let's say, boxes that you might want to have. For example, for a traffic sign, I'll use something like this. For a person, I might want to use something which has a little bit of a different ratio of width to height. For a car, I may use something which is almost a square or something like that. My model is training very slowly. I could increase the learning rate. I could add a layer. I could switch on or off different parts. I could present different ways of data augmentation. There is a thing here. Where was it? Somewhere at the beginning. Oh, here. It's on the first stage. These things present you with the kinds of images that you have, what sort of augmentation you want to apply, rotations, translations, scaling up or down, flipping. Flipping, by the way, is not very common for self-driving cars. Your camera might not be upside down or shouldn't be upside down. You might want to apply regularization and many, 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 many other things. But all of these are just technical. And here's the power of the API. Yeah, it was pretty hard to start. It was. And if you try it out, you'll see it will take time. But after that, you're able to do a lot of things. Okay, I hope this will get you started. A lot of people have asked me, it is a pain, I know. Keep in mind that G3doc has nice documentation. Also, don't be afraid to look at different things. For example, there's a folder called Protos here, which describes all of the things that you put into the file, into the configuration file. So, for example, if you have the image resizer, these are all of the configurations for all of the different kinds of image resizer that you might want to have. And there we go. There is our image resizer. So this is it. I hope you can get started. I hope you don't get scared. By the way, how do you get started? Use Google Colab. It's free. Oh, unless it disconnects you, of course. It's free. It's very easy to use. And it's very, let's say, beginner friendly. There are some restrictions to it, of course. But in order just to learn, you could always use Google Colab. How do you get started? Download the dataset. Choose a small subset of the data. Do not train on gigabytes of data at a time. Resize it down in order to make training faster. Start out very simply, maybe even with something that you could implement yourself. Then go step by step, from the beginning toward the end, not the other way around. I'll be very happy if you send me your models, or if you send me your concerns, or if I am able to help you at all with your endeavors. My email is right here. And you could always reach me here, or on LinkedIn, or even someplace else. I don't know. I'm not that hard to reach. If you have any questions, I'll be very, very happy to answer them. If you have any problems with your model, I'll be happy to try to get you started. And here's the small secret. All of the things that we talked about for object detection apply to semantic segmentation. There is a model called mask Rcnn, which is essentially an Rcnn working on pixels. And it's a part of TensorFlow models. It means that means that it's absolutely trivial to use it once you're acquainted with all the quirks with the TensorFlow Models API. Okay, thank you very much. I know that we are almost at the end of the lecture, and I want to ask, are there any questions for me? Because I'm not able to see the stream.
Hi again from mine. So first of all, thanks again, Dan, for your time and all the interesting details that you shared with us today. Actually, I see that the audience seems to be a little bit shy, maybe, and hasn't sent a lot of questions. But I have one related to Rcnn, since you just referred to that again. Is there any metrics that could give us some more details on some ratios? For example, cycles per pixels, or to orient us a little bit more what slow means actually. How slow is slow, for example?
How slow is slow? Well, what do you mean in terms of runtime performance?
Yeah, because you mentioned something about performance in that.
Well, not exactly sure. There is the model detection zoo, which I showed you, and this is the performance. This is the speed in milliseconds that all of these different models use, but those speeds can vary. For example, it's very easy to reduce the speed by a lot by resizing. If you resize an image to be from not, let's say, 1,000 by 1,000, but 500 to 500, you reduce it 4 times, and you increase the speed by more than 4 times sometimes. It might be a little bit less, but it's something like that. If you want to, there are many metrics, by the way. There are many benchmarks on many different data sets. If you want to see, you better see it for yourself on your data set. Other than that, I could recommend something called Papers with Code, which has all sorts of metrics. So if you go to data sets, and for example, semantic segmentation, let's open this one. And here we go. There's our Cityscapes dataset. And you can see how different models perform. So you can see this paper, which is, I think, the one by NVIDIA. And you can see the state of the art. You can see how good they are. And in some cases, you can see what time it took. In this case, unfortunately, we don't see that. But we can at least see how good the model performs, how well the model performs, sorry. Timing is usually done on a very laboratory kind of setting, and it's going to differ quite a lot.
Okay.
Yeah. Yeah. This is a philosophical one, I think. Well, okay. As I said earlier, the scientific answer would be, I'm not sure. But I do have a preference. And my preference is going to be with a simpler approach. Of course, when we give more senses to our car, it's going to sense its surroundings better. But it in turn comes with much lower performance. Excuse me, could you step back from the microphone a little bit, please? So there is this trade-off, and speed is of crucial, utmost importance. I would bet on having maybe binocular cameras, which means stereo cameras, or even maybe a larger field of view, but vision should be enough, in my opinion. Why should it be enough? Because of the processing time. If we have the processing time to have sounds, depth sensing like LiDAR or even infrared for parking, which is, by the way, a different topic. What stops me from having a different subsystem for parking, which I'm not using while driving? Parking is a very, a relatively safe and relatively slow process. I don't need to process all of those kinds of things. So yeah, for me, it's all about vision. I might be a little bit biased, but I think having the vision modality implemented in a very, very, very good way, good, fast cameras, fast algorithms, etc., would be enough. And also it's going to reduce costs. Yeah, a lot of questions here. Well, in general, yeah, that has to translate. The problem is they're different environments. By the way, robots do have quite good environmental senses, environmental awareness, if you will, because their environment is quite constrained. Let's say a robot produces microchips. It can't move that far away. Or robots getting your groceries, deliveries, etc. These kinds of environments are more constrained. They're already susceptible to automating with reinforcement learning approaches. What I am not sure about regarding your question is, if you will, is your environment is quite constrained. Let's say a robot produces microchips. Sorry?
Yeah, hello, you're done. I think something happened with Jana and Todor. So
just a second to finish my sentence, please. Sorry about being that rude. For me, yeah, if we solve self-driving cars, we could translate the sorts of thoughts. We could use transfer learning or something like that. The problem is, will we ever do that? I don't think things like awareness are able to be coded in a differentiable loss function. But if they are, of course, that's the goal of it, and we are working for it. Yeah. Hi, Sergey. Oh.
okay. So sorry.
Oh, while Sergey appeared. Oh. I'm not allowed to. Sorry. There's some things called non-disclosure agreements. Or was the question, can I share a good practice of what I've done with self-driving cars? Oh, for debugging? Oh, sorry, I didn't quite hear you. Well, there are different tools. There are different explanation tools based on like Shapley values, things like that. We are very, very big fans of something called a heat map, or let's say attention points. We could, for example, see which part of the image does the model pay attention to. And for example, to say if something is a traffic light, does it actually take its attention to the traffic light, or does it look elsewhere? So we could do something like that. We could do some model explanations. For example, what does a certain layer do? Does it, for example, recognize ice or something like that? We have all those sorts of tools to help. Okay, I'm going to show you one. It's called an activation atlas. If I can. Atlas, what's going on? I can't type. So here we go. It looks something like this. It's all-dimensional embedding of a very high-dimensional space, but you can see how images go, for example, on this dimension. For example, they might go from red-haired dogs to black-haired dogs. And this is something which helps us understand what a particular layer of the neural network is doing, and whether it does random stuff, or for example, whether it really, really understands what's going on, whether it really finds parts of dogs or dogs or traffic lights or whatever. So this is one thing that we love doing. I'll try to show you attentional saliency map. It's called a saliency map, but I'm trying. Okay, this will work. I'm trying not to use the professional term here, but here's what it looks like, but not for human eyesight. It's rather for the model. And we can see what parts of the image the model pays attention to, although this kind of pays attention is very abstract. But there are things which produce higher responses. So all of these are methods to evaluate the model, and there are many different methods to reduce biases, which are even more important than that. That's what we are using for debugging. Keep in mind something else, though. It's always about the researcher. It's always some outside kind of metric. Statistics cannot present you with bias, cannot present you with a metric on bias. It's always something outside, and always something related to your experience as a scientist. So how do you debug neural networks? Simple answer, you can't. Complicated answer, it's complicated. There are many ways, but none of them work perfectly. We are over by 10 minutes. I apologize.
Yes.
I apologize profusely. And thank you for staying with me, everyone. I'm extremely grateful for you. Appreciate you being here.
Yep, and I also thank you for accepting our invitation once again and taking time to share those interesting details with everyone. So I think that this is a good time to close the meetup as we're already ahead. Thanks everyone for being part of this event. Enjoy the summer, and we'll catch up again soon. We have a beer in month August, so hopefully we'll be able to see each other there.
Okay, thank you so much. I think this is a really exciting and nice place to be. I mean, an hour and a half to get started with self-driving cars, I can take it. I hope to see your projects, your questions, etc. on my email or LinkedIn. I am very, very grateful that Data Science Society exists, and all of the great people that work and participate there. If you don't know about them, check them out. It's worth it, really.
Okay. Thanks, everyone. And yeah, hope to see each other again soon. Bye.
Bye-bye.